So first a little bit, I would like to explain about what Midas is, what it does. For those of you who do not know, Midas IT is one of the leading CAE software developers and distributors in the world, and it has been in business since 1980, in the business of CAE since 1989. We currently have offices in China, USA, Japan, India, UK, Singapore, and we are ever expanding and ever growing. So this slide shows some of our major products in the field of computer-aided engineering. So we cater to every major CAE industry that is out there. So we have products for mechanical, for building, for civil or bridge engineering, and even for geotechnical engineering. So the product of our discussion today will be Midas Gen, our building engineering product. Simultaneously, I will be showing you a little bit about our new member design tool, that is Midas Design Plus. So before going, I'd like to just explain a little bit about the versatility of Midas Gen. So these are some of our past project applications that have been taken using this product. So as you can see, the Beijing National Stadium, the Bird's Nest Stadium for the 2008 Olympics. We have other stadiums like the Seoul World Cup Stadium, the Jeonju Stadium, and the various pavilions at the Olympic Games. Aside from this, Midas Gen can also handle structures like airports, transmission towers, cranes, pressure vessels, even things like machine structures. So Midas Gen is not limited to purely buildings. It is an all-purpose tool that can be used to model and analyze just about anything you might want to throw at it. Now, these are some of our more high-profile projects. So the crown jewel of our project applications, that is the Burj Dubai, now it is called the Burj Khalifa, so in UAE, which is currently the world's tallest building, the Guangzhou Twin Towers in China, and Moscow City Palace Tower, or also known as the Twisting Tower in Russia. So let's come on to the contents of today's presentation. So I'll talk a little bit about the design features of our software and give you a brief demonstration of how a model can be created in the software. Then we'll come on to the AISC code itself. I'll talk about the things in the ultimate limit states like load combinations, tension provisions, designing for compression, checking for buckling, for flexure and lateral torsional buckling in beams, checking for shear. And finally, I'll talk about serviceability limit states, wherein I'll discuss chiefly about deflection and drift limitations. So let's come on to what our software can do. In this slide, you can see the various design features that our software possesses. So we have a complete bevy of design features that can cater to all the requirements of a building engineer. So we have steel code checking, steel optimal design, which I will come to later in this presentation. Furthermore, we also have RC design, and limited provisions for footing design are also available. This next slide shows the available design codes that are there in Midas Gen. So as you can see, for steel design, we not only support the LRFD code, but we also support the AISC ASD and the AISI CFSD codes as well. For footing design, we have ACI 318, and for RC also we have the ACI 318, and similarly for slab design as well. So the American code implementation status at present in Midas Gen is as follows. So we have the complete data material and section database for steel and concrete as per AISC and ASTM. We have the static wind load cases as per ASCE 7-10, static seismic loading, and the response spectrum functions as well. Furthermore, we have all the auto generation of load combinations and steel frame design and slab and wall design as well. So let me now come over to the software itself. So I hope you can see the software now. So I'll just give you a very brief demonstration of how easy it is to create a model in Midas chain. So this is the model that we'll be creating today. It's a steel building model that has about 5 stories, and I'll be importing the floor plan from AutoCAD, and I'll be assigning boundary conditions and loadings to it. So let's open up a new file and let's start. So here I'm just importing a DXF plan. So with this, my floor plan has been imported from AutoCAD DXF file. Now I will commence to create the first basement story. So what I'm going to do is, first I'm going to create the columns. I'm just going to extrude the nodes. So let's say my basement level has 3.5 meter high columns. So I hope now that you can see the columns have also been created. Up next, in the works tree. Now the works tree of Midas is a very useful feature that shows the status of your project. So anything you do in your project will get highlighted over here. And here you can see the material and section properties are undefined. So let's go ahead and define some properties. Let me say I define a property called column. I assign it the steel property A53. And I assign a section property for column as well. So in section properties, all you need to do if you want to go for a database section is you can just choose the database you want. For example, I'm choosing AISC 10. And here, once you've chosen the database, you get a complete list of all the database sections that are available under that particular section, under that particular database. So let's say I choose W40 times 183. So as soon as I apply it, the model is now updated. Let me add more materials. For example, here I add a material for beam and brace. So I'm going to apply the same material to the beam and brace, A36. And let me create 2 sections, one for beams and one for brace. Okay, so now this is one of the more difficult parts of a lot of modeling, so a lot of structure analysis software, that how do you change the section or material properties. So in Midas it is very easy. You just select something and drag and drop. That's all I did. I just selected everything that I wanted to select. For example, for the beam sections I want to put the beam property, so just drag and drop the beam property. Okay, now let me, before going on to brace, let me just say that since here all the columns are oriented in a single direction. Now in a building it might be that you want to orient some columns in a different direction to have more rigidity, to uniformly distribute the rigidity in both the X and the Y directions. So if you want to do that, so here I'm just selecting all the columns whose orientation I wish to change. So let's say like this. So I've selected the columns whose orientation I want to change. And I'm just going to change element parameters and changing their beta angle to 90 degrees. So once I close it, so here you can see that indeed the selected columns orientations are now different. Okay, so finally we'll go over to brace modeling. So I'll just create an element, material beam and brace, and the section property as brace. And one brace over here as well. So with that, our first story plan is done. Now let's create some load cases. So the load cases I'm going to create are case for dead load, case for live load, wind load in X direction, the wind load in the Y direction, and similarly earthquake loads in the X and Y directions. So once these load cases are done, I'll very quickly assign my self-weight just from here. I only need to specify the direction. Since the program already knows the material properties and the volume, it has the self-weight. I only need to specify which direction the self-weight will act. Then I apply the live load. Now, by rights, I should be applying the live load after creating the entire structure. Now that is also possible, but here I will show you one very easy way of applying the live loads. So here I'm just applying a live load of -2 kN per meter to all the beam elements on the first story level. And once this is done, we go over to building generation. Now the building generation wizard feature of Midas very quickly allows us to create a building from just one story. So you can think of it as a copying option. You just copy one story above, over and above the other stories. So let's say I want to have 5 stories at a distance of 3 meters each. So I select everything and click apply. And once I do this, you can see my entire structure has been created. So the building wizard also holds functions for in case you want to have different material at different story. So that material ID, section ID, properties, they are there for changing the material at different stories. So very quickly, let me also conclude the wind load and static seismic load options. So for wind loading, Midas Gen supports the IBC 2012, 2009, 2007, and even the UBC, ANSI, the NBC code. So all the major wind load codes are supported in Midas. So let's take IBC 2010, 2012. So you just specify the basic wind speed at in miles per hour, your exposure category, the mean roof height. So in this case, we'll have to take the height of the building. So it will be 15 meters in this case. You can take any topographic effects if you wish. And since this is in X direction, so I'll put Y direction as 0. Now, my apologies. Before going into the wind load generation, let me first do the story data. So the story data feature is actually necessary for wind and static seismic generation, and it also has these basic features wherein you can use the ground level. So when you specify the ground level, what happens is that everything that is at that level or beneath that level is disregarded when you go for wind or static seismic loadings. So here you can see we have the basement level and we have the first floor, second floor, and so on. Two things I would like to point out here is that the floor name designation is in terms of first floor, second floor, and so on. So in countries where the ground story is termed as a ground floor, so you have to change the name manually. Since the software is a Korean software, and here in Korea the convention is that the ground story is termed as the first floor. The other thing that I would like to point out is you can see here floor diaphragms. So floor diaphragms basically are automatically created when you go for the auto generation of stories. So floor diaphragms basically mean that you don't need to model your slab. However, if you do want to model an RC slab, you can do so using the plate elements, and in that case, you can just choose the do not consider option. Similarly, you also get the data for wind and seismic generation options. Okay. So once this is done, let's go over to the wind load. So as I was saying, the mean roof height is 15, and here let me put this as 0, and once this is done, you can actually get a very good idea of the wind load profile. So here you have the option for story force, story shear, you can check the overturning moment, and you can even make a wind load calculation sheet. So this is basically a report of the wind load calculations as per the code. So all the equations that have been used, they are shown over here, and the final calculations, any notes that have been made. So you can just directly take this report and put it in your overall complete report. Okay, so let me apply it under wind X. Similarly for wind Y, I'll just change the direction factor. So X is 0 and Y is 1. Now for seismic loading, I first have to go and create some masses. So I'll just convert my self weight into mass, and then I'll go into the static seismic loads. So for cases where seismic loading is very important, the engineers may find this very interesting. So again, all the important static seismic load cases are covered. So you have codes like the IBC, UBC, NBC, the Indian standard, the Taiwanese, Korean, and Euro code also is available. So just select the code that you wish to use, select the relevant parameters under that code. So for here we have to give an approximate period for our structure. So you can select from the predefined options. So here a lot of predefined options are available. You can select from any one of them. And once this is done, you get a very similar kind of result dialog box that you got for the wind load. So everything is again here. You can get story force, story shear, overturning moment, and you can even combine them in SRSS form, and you can make a seismic load calculation sheet as well. So again, it gives you all the calculations with the relevant equations that were used. Okay, so let me just very quickly apply this in the Y direction also. So all our loadings are done. Now a little bit about certain boundary conditions that are important in buildings. Now, in the case of buildings, you might want to go for like, let's say, for an initial analysis, you might want to just go for a fixed support at the base. But in case of very tall buildings or very important structures, you might want to consider the foundation at the base as well. if that is your if that is how you want it, then you can very easily model the foundation in Midas, and to assign the boundary conditions, we have these several options. So here you get the option of pile spring supports. So particularly for pile foundations, if you have a pile raft foundation, so you can directly automatically create the pile spring supports. You just need to enter the coefficient of subgrade modulus and choose the initial soil modulus type, your soil type from here, if it is sand, soft clay or stiff clay, and you can very quickly create multilinear links which will be capable of performing limited soil structure interaction in Midas Gen itself. So you can perform a very preliminary geotechnical analysis within this software also. For now, considering just a preliminary analysis, let's just very quickly create fixed supports at the base. Okay, now another thing that happened is, you will remember that under story data, we checked the consideration of diaphragms. Now that is a rigid diaphragm, and by default, it is being extended across the entire width of the flow of the story. Now, the problem is that we have an elevator shaft here. So there is no slab going through the elevator shaft. To account for this incongruity, what we can do is we have this option called diaphragm disconnect. So on using this option, what happens is you just select some nodes and apply it. So whatever region that is bounded within these nodes, that will be removed from the diaphragm. So it will be as if there is no slab in between these nodes. So the elevator shaft is clear. Similarly, if you have a staircase or a stairwell, so you can directly use the diaphragm disconnect to model that as well. Finally, let me just zoom in over here. Now, I think every engineer, every attendee here will know this, that in finite element softwares, the results are calculated right at the nodes. And in case of this, like for here, you can see the node is at an intersection of 3 different members. So almost every code specifies that you have to consider the bending moment not at the center of the nodes, but rather at this cross section, that is the panel zone. So the panel zone effect has to be considered. Now in Midas, we have what is called the automatic consideration of the panel zone effect. So here you can see we have an option called panel zone effects. So with this option, you can automatically calculate the panel zone effect, and the Midas will automatically figure out where the panel zone effect is, and it will design just for that, and it will show you the results at the panel zone. So you can see the panel zone effect as well. So with that done, let me just go over back to the presentation itself. So now let's come to what the code says. So AISC LRFD 2010, that is the 14th edition, is currently in its 14th edition, and there have not been too many changes since the 13th edition. So the particular references that are made here will be made to the AISC specifications, ASCE specifications, and certain other specifications that will be detailed within this presentation itself. So first off, let's come over to the load combinations. So the ASCE, the ACSC 710 clause 2.3 and the appendix C state the use of the following load combinations that you can see here. So 7 combinations under ULS and 4 under SLS. Now, considering direction as a factor, these can be even more than 7. For example, wind load can be treated separately in 2 directions. Earthquake load can also be treated separately in 2 directions. So depending on that, more combinations are made available. So coming on to tension, now the resistance of cross sections. So first of all, the first provision in the AISC specifications is about tension. Now design tension resistance is given in terms of either the yield strength or the ultimate strength. So in terms of Midas Gen takes it in terms of yield strength, and since Midas Gen is not able to do connection design, it does not consider the ultimate strength. However, this is considered in our complementary software, that is Design Plus. Coming on to compression. Now, in compression, whenever we talk about compression of columns or compression members, immediately, particularly for steel, buckling comes into mind. So buckling is a very critical phenomenon for steel members in compression. And in case of for classification of sections, for compressional buckling, we have to classify them as either slender or non-slender. So this classification is actually detailed out based on the section dimensions or the width to thickness ratio that is detailed in table P4.1a. So when we come to flexural buckling for non-slender elements, we have the following parameters. Now this the compression resistance or the design compression resistance is given out in terms of the elastic buckling load, that is the Euler buckling, and the yield strength. So in the equations to the right, you will see Fy by Fe. So depending on what is the yield strength of the section used, and what is the value of the slenderness parameter KL by R. Now, a question comes: how do we calculate K? Since we know what L is, we know we can calculate what R is. How is K calculated? Well, AISC specifies two basic methods. One is that it gives you tables that you can refer to for calculating the value of K. The other method is given in Appendix 7 of the AISC specifications. This procedure, I should say, is also available in Midas Gen and follows from the research of Ballio and Mazzolini in 1982. So this is how you can calculate the K factor, the effective length factor for columns, and Midas Gen can do this automatically. We have an option called auto calculate effective length factor. When you check it on, the length factors are calculated automatically. Now, what about when you have combined compression and flexure? So the previous sections were just for flexure for buckling under compression. So if you have a flexure load acting as well, the classification itself becomes slightly different under the AISC code. So here the classification becomes in three types. You have compact, non-compact, and slender sections. So as everyone knows, compact sections are those that can achieve full plastic moment. Non-compact sections can only achieve elastic critical moment, while slender sections buckle even before reaching the elastic loading. Once again, the AISC continuing its trend of very user-friendliness gives you very quick reference tables on how one can calculate the lambda P and lambda R limiting parameters for calculating the compactness ratio. So the width ratio B by T, here you can see it can be easily calculated. So combining the torsional and flexural torsional buckling for once again for slender and non-slender elements. So here the FCR takes a slightly different shape. So FCR value is different for different kind of sections. So for doubly symmetric sections or double angle and T-shaped compression members, and also for singly symmetric sections. These are the equations that are specified by the code that you can see in the slide before you. For slender elements, it is pretty much the same as for non-slender elements. However, there is an additional factor called a Q factor. So the Q factor is basically a reduction factor that is there for the slender elements, And it is basically there are two kinds of K factors that are specified in the code. You have QS for the unstiffened and QA for the stiffened elements. So a little bit of information about elastic and inelastic buckling. Now, everyone here knows that elastic buckling is basically Euler buckling, that the formula pi square EI by L square is basically only applicable for long and slender columns. Now, when the column is slightly short or of intermediate length, or the section properties are slightly large, that is relatively non-slender, in that case, buckling can happen in an inelastic form. So the limitations for inelastic buckling have been researched and have been discussed at length under the AISC code, and basically depending on the KL by R ratio and also the yield strength of the steel that is used, we have different limits for the elastic as well as the inelastic buckling criteria, as you can see in the slide before you. So for example, for the red curve in this graph here specifies for Fy equal to 36 KSI, wherein the limiting KL by R ratio is 113. So for 36 KSI, if KL by R is greater than 113, you have elastic buckling. Whereas the same thing, for 134, whereas the same thing for Fy equal to 50 KSI, you have the elastic buckling limit at 113, while that for 36 KSI is at 134. Coming on to the resistance of cross sections under bending moment. So bending moment criteria, bending moment resistance in AISC is specified in terms of either the plastic moment of resistance or the yielding due to lateral torsional buckling. So whichever is the lesser of the two, that becomes the limit, that becomes the strength of the section. So AISC specifies very extensive equations for calculating both of these criteria. So M plastic is very simple. It is just yield strength times the plastic section modulus, while for the resistance for the lateral torsional buckling, there are different formulae available that I will show you in the next slide. So here you can see a very quick and good comparison of the lateral of the moment capacity under different kinds of criteria. So it is the moment capacity will be the highest for your plastic moments for the plastic sections. It will be slightly lower for the region of inelastic buckling, and the lowest under the elastic buckling. So one thing that has not been discussed is the length parameter. So we have in this graph LP and LB and LR. So LB is basically the unbraced length, and LP and LR are calculated based on these criteria that are shown in this slide over here. Coming to shear calculations. Now again, shear in a similar fashion to moment is based either on the limit state of shear yielding or on the limit state of shear buckling. So the formula is actually very conveniently the same, similar I should say, for all three, for both of them, for both yielding as well as for buckling. Now in the case of shear buckling, it is only the parameter CV that undergoes a change. So you can see very clearly in the graph that I have shown in the slide that up to a certain parameter h by tw, the section yields under the limit state of shear yielding, but after that it begins to yield due to shear buckling. Coming finally under ultimate limit state to combined flexure and axial force check. So the AISC code classifies this very broadly into three different categories, that is doubly and singly symmetric members, unsymmetric members, and members subject to torsion, combined torsion, flexure, and or axial force. So in the case of symmetric sections, this is the equation that is used. Basically, these are all interaction equations, or rather variations of the same interaction equations. So they will all be like, they will all end up being less than 1. So here, the basic theme of all the equation is the requirement, the required parameter upon divided by the available strength plus other required parameters divided by other available strengths should combined be less than 1. So this here is, you can see, so PR is the required axial strength, PC is the available strength, similarly MR is the required moment, MC is the available moment. Similarly, for asymmetric sections, you have flexure and compression/tension. So it is following much the same format as of the normal interaction equations. Finally, when we come to seismic load resisting systems, so under the AISC seismic provisions for structural steel buildings, we have the following kind of seismic load resisting systems that are defined by the code. So special moment frames, intermediate moment frames, ordinary moment frame, special constructive brace frames, buckling resistant brace frames, and special plate shear walls. Now, very conveniently, Midas Gen has support for each and every one of these load resisting systems. So before moving on to serviceability checks, let me just come over and let me show you some of our design features of our software. So let me open up a new model. And I will quickly walk you through how easy it is to conduct steel design in Midas Gen. So first of all, let me explain a little bit about this building. So it is an RC frame structure, a steel frame structure, as you can see over here. And let me show you some of the load combinations that have been created. So let me recreate these load combinations. When I click on auto generate, I can simply select the code according to which I want to generate my load combination. So AISC LRFD 10 is already there. And when I click OK, so all the load combinations are automatically created. Now, if you want to use a design for a user-defined load combination, that can also be done. So you can design or you can check for your sections for your user-defined combinations also. Furthermore, under definition of frame, you will notice, as I had explained, you can check whether this whether your frame structure will be braced or unbraced, and whether or not you want to auto calculate the effective length factors. So if you go for auto calculation of effective length factors, they will be calculated accordingly. So under steel design parameters, you can just select your design code. So if you want all beams or girders laterally braced or unbraced, you can just check it. And here, from here, you can see and you can select what kind of seismic load resisting system you want to choose. So you can choose to modify your steel parameters. So here you can modify any parameter. For example, if you have a user-defined material in your building, or if you have material, for example, if you're using the American code but not the American material, you can actually choose or replace the material of a different code from here. So for example, if you're using the BS code materials, you can choose the BS code from here, and you can choose the relevant material type. Finally, the seismic load rating resisting system. So here I can just choose from here the load resisting system. I can select which systems, for example, if all my bracings, let's say, so all my bracings are part of the resisting system, I can just simply add them as part of the bracing system. So once this is done, I can simply go ahead and do a very quick steel code check. So while the code is being checked, let me very quickly come over to serviceability checks, and let me discuss serviceability checks as per the AISC code. Now, the AISC code is actually a little bit vague when it comes to serviceability. Most of the we do not have any set limitations, but rather just simple provisions. For example, the ASCE code commentary says that a deflection level of 1/300 for beams and 1/150 for cantilevers is visible. So it does not actually give you any direct limitation. Now, normal limitations that are prescribed for floor construction by various authorities around the world are, for example, for plastered floor construction, you can have the limitation as L/360. For unplastered construction, it should be L/240. And for unplastered roof construction, it should be L/180. And regarding drift checks, so in terms of drift, basically the horizontal deflections contribute to the drift in the structure. So for example, the wind loads, the static seismic, or the response spectrum loadings. Now, in terms of low-rise steel structures, drift limit is imposed between h/60 and h/100. So in terms of, so h being the complete height of the story. So in terms of percentage, you can normally say it like, for example, this is between 1 to 2% of the total height of the story. I'm sorry. So no, and this is very usual in the case of buildings. For example, in terms of RC buildings, even it is usually at 1.5%. So let me just go back to Gen. So now our section has completely been designed. Our building has completely been designed, and now you'll notice there are some sections that are not good. So let me come back to these later. Let me first show you some of the very useful features. So for example, if you want to check on a section in more detail, you can just click on the graphic option, and for that particular section, for that particular property, you will get a very brief design or check report. So this report can be directly printed or can be saved. So here all the checks are performed. This is like a summary report basically. Furthermore, and this is perhaps the most greatest option in Midas. Now, in a lot of softwares, the design process is a black box. What this basically means is the design software will just give you the results. It will not show you how it got to that result or what equations it used. Midas Gen gives you everything. This is a detailed calculation report that is available for any kind of design in Midas Gen. That is, you can have RC beam design, steel beam design, column, slab, wall, anything. So this detailed calculation report shows you exactly what the program is doing and even shows you what specification of the code is being referred to. For example, this highlighted line that I am showing you, it reads AISC 14th specification B4, table B41B. So it tells you exactly which specification, which clause it is using. And Of course, all the equations that are used are also specified. So any engineer can easily check the validity of the detailed report. And in fact, you can directly copy paste this report into your final report and use it like that. Okay, so that was about the section. Now, coming on to those sections that were unsafe. So let me just show you a little bit about that in our presentation. So Midas Gen provides two different methods for optimizing or for changing the steel design, or the steel section. So you have the first method as the automated optimum steel section selection, and the second method is manual updating of the sections. So what I mean by this is, let me show you the software. So in manual updating of the sections, what you do is just select the section, click on change. So from here itself, you can simply select a different section. So if I click on search satisfied section, so it will search for sections that are able to resist the same amount of loading that this particular section is experiencing. So it will give you a list of all the sections that are available. So for example, let's say W16X or W18X40. So if I click on change and close, so it will automatically change that section directly from here. And if I say update, so I can directly change the section property and update it. And once the design is redone, so it will basically change that section property and it will redo the recalculate. And it will show that the section is indeed safe. The other option that is available, so let me show you that other option now. So that other option is called steel optimal design. So under steel optimal design, the program does an initial check of the entire member or all the selected members. And once this check is done, it will finally give you at the end of it a summary of whatever needs to be changed and whatever needs to be updated. Now, the very useful feature of the steel optimal design is that you can actually reduce the weight of the structure. So here you have the sections, and here you have the sections that require changing. So let's say I select all, I put it through one repetition and just put it under design and analysis. So what Midas Gen will do now is it will basically search for optimal elements that can replace the existing elements, and it will at the end of it give you a final redefined element position, redefined elements. And once you update them, if you find it that they are useful, if you find it that they are okay, so you can just update those elements, and you can actually even see a comparison between the two to find out whether or not the weight is actually being reduced. So here you can see the reanalysis is being undertaken. And once more, Midas will do a member check. And once the member check is complete, it will give you a complete and full detail of all the changes that have been made and also of the comparison that was done. So one final reanalysis. And finally, we can get the section data. So here you can see, I don't know if you can see this, but some of the sections have actually indeed been changed. So here you can see like the optimal design results. So because of the change of the sections, the forces have been redistributed, and some of the sections are, some different sections are now basically failing. So initially we had 3 sections that were failing, but now we only have 2 sections. So those sections can be manually checked, or you can just check them automatically by redoing the analysis again. If you want a graphical update, so let me show you the graphical update of it. So as you can see, for some it reduces, but for some it increases because of the because some sections are failing, so the section weight needed to be increased as well. But if your section, if most of your sections are passing, if you change the sections once they pass in the second iteration, as you can see for the green lines to the right, the section weight is also reduced. So you can also compare this over here so that the final section weight can be reduced. So this was about the optimal section analysis. And in the detailed report, the seismic design check is also performed. So once you go for the detailed report, the seismic provisions are actually also checked against. So here, once again, this is the slide that shows more details about the optimal design feature. So the optimal design feature, as I've already mentioned, is very useful if you want to reduce the weight of the overall structure. And all section dimensions are usually within plus minus 5% of the within the plus minus 5% of the original dimensions in one iteration. So this is how you can use this function. Now let me come over to our other software, that is Design Plus, for member design and connection design. So currently Midas Gen does not have the facility to go for direct member design, as I had mentioned already. This facility is available in our software Design Plus. Now for those of you who have attended our RC webinar section, they will be aware of what Design Plus is, but for those of you who do not know it, it is a very recently released tool that can very quickly allow you to go for quick member design. For example, here you can see the various member design options that are available. So under RC, you can go for slab, beam, column, general columns, corbel, bracket, staircases, footings, patch wall design, and so on. And for steel, we have bolt connections, base plate design, beam and column design, web openings, and purlin and girth. Okay, so let me go for simple beam column design. So this is the interface of Design Plus, the first time that you open it. Now Design Plus can be used either as a standalone tool, or it can be used in conjunction with Midas Gen. So if you want to use it with Midas Gen, you can just link it to Midas Gen. So we have this Midas link. which allows you to link with an existing Midas analyzed file. And let's say I select a column. So let's say I've selected this column. So in Design Plus, automatically it gets registered as the member ID. I can import it. And let me just check an option here. So here when I import, I can choose either the design options, either I can choose it as by all, or I can choose to use the options from Gen. So I'll choose min max forces all, re-import it. And here you have all the relevant parameters. Okay, so let me enter its length. So here length is 5 and the brace length is also 5. So I'm basically entering some basic parameters over here, and since the loadings are already there, I can even go for checking of torsion. But since the loadings are already there, so here you can check the load combinations that are there. The various load combinations can be checked, and the maximum of these load combinations is used. And I can perform a basic check. So once the check is done, I can see whether it is complying with the check or not. Similarly, let me go back to Gen, and let's say I select a simple beam. So once again, I can import this. And since it's this is a beam design, so let me again go for some design checks. So here I can just recheck the entire thing. Now, why would I want to, since already Gen has created the design for me? So there is no, you might feel that there is not too much advantage in going for a similar design in Design Plus. The only thing is here that you can do is that you can get a very detailed report. So here you get a report of the section. So you can get a detailed report or a summary report. So let me show you what the report format is like. So for example, here, this is the report format of the member design using Midas Design Plus. So the entire member is checked, and all the equations again. So here you have the interaction checks that I used, and shear capacity checks and so on. So all the basic checks are used, and it shows in very good detail. So if you want a word path based file instead of a text based file, so you can go for Design Plus in that sense. Furthermore, we have the option of creating engineering drawings within Midas Gen. So if you go for create drawings, so it will give you a list of drawings like here. For example, it will just, since there are no shear connectors or anything over here, it will just list out the sections like so. And similarly over here, it will list out the sections as well. So right now, the code that I'm using is of course the American standard. So from here, you can change the code also. So currently Design Plus supports the American code very completely. It supports Eurocode also, but has limited support for Eurocode. Let me go over to base plate design. So base plate, for example, if you, in case you want to have the eye girder connected to the foundation with a base plate. So what we can do is, we can just go over here, select a node, and just import it. So here you get the base plate as well. So once I just go for the anchor bolt, I can see whether all the parameters are here. They are all very visible. I can just check whatever I want to design for. And when I click on design, so Midas will do an FEM analysis internally, and it will design for the base plate. So here you can see that some parameters are failing because of the dimensions that have been used. But Here you can, but the bigger picture here is you can very easily check for the base plate diagram. So MXX, the base plate shear, the wing plate moment diagrams, and so on. So it is a very detailed report of everything. And speaking of detailed reports, this is the report for the base plate design. So as you can see, the general reporting, the images and everything are very clearly highlighted, and all the calculations that are being done, so bearing stress, calculate, check bearing stress of concrete and so on. So everything is done very clearly and very concisely. Okay, so that was about the base plate. Coming on to bolt connections. So the connection that is actually defined in Midas Gen at present is the shear connection. It is not a moment connection. That will be incorporated in future versions of Design Plus. But looking at the shear connection right now, so once again, let me just import some sections into Design Plus. Okay, so here you can see checks for bolt connections. So if you go for a quick design of bolt connections, it will very quickly redesign with the required number of bolts. And it is here that you can recreate your drawings very easily, and it gives a lot of detail in the drawings as well. Furthermore, you can of course always save these drawings in DXF or DWG format to be used in AutoCAD later. Okay, so the other things that are there in Design Plus for steel design are like web openings, purling and girth, and crane girder design as well. So I will not be going into those in detail during this presentation. Let me revert back to my presentation, and let me come to you with the final topic of today's presentation, that is BIM. So Midas Gen has very good interoperability with BIM tools like Revit and Tekla. So today we shall be seeing how to import a model from Revit to Midas Gen and then export it back again from Gen to Revit. So what all are the things, what are the changes that are made, that can be made? So if you have imported a model into Gen from Revit, the sections will be changed. If sections are changed in Gen, they will be changed in Revit. If elements are deleted, the same changes will be made in Revit. Movement of elements, addition of elements, changing the orientation or the beta angle of elements, and changing any material properties. So these changes can currently be made. And come early June, we shall be releasing an update to our Revit link, wherein we will even be able to modify the boundary conditions, the static loadings, and even the load combinations. So it will be a very complete link between Revit and Midas Gen. So at present, let me show you a Revit model that I have with me. So this is a Revit model that is made out of steel sections. So I'm sorry if there is a bit of glitching, since Revit is actually very slow on my system. So here you can see the UC universal column, steel eye girder column that is here. So let's export this into Midas Gen. So using this dialog box, I can send the project into Midas Gen. Okay. So once I send this, it will basically rewrite the thing. And let me open Midas Gen now. So let me open a new file. So it will basically send the file into Midas Gen, and I can import a gen mgt file. So it is in the process of sending. So once it sends, okay, so it says that sending has been done. I can simply import the model. I'm sorry, let me import okay, so here you can very clearly see how the model looks like. So we have I sections, and all the sections that were there have all been imported. Now we can make changes to these sections. We can make modifications to these sections anyhow that we want. So for example, if we change any section properties, we can do that from here directly. So for example, S275, if I want to do it, I can just do S275, or I can change any of the section properties as well. So maybe let's say 400 by 400. And once the changes are made, I simply export the genmgt file again. And then I can re-import this back into Revit using this feature called update model from Midas Gen. Okay, so since the update feature will actually take a very long time, as I explained that Revit is very slow in my system, and it is not working very well since it is a 64-bit system. So let me instead show you in the presentation how it will look like and how it will finally be. So once the sections and everything is importing is complete, this is how it will look like. So a window will pop up giving you an update summary. So it will tell you all the modifications that were done. So 65 new sections were assigned, 1 new thickness was assigned, and 2 modifications were made to the section. So it will give you a very complete list of all the modifications that were made, and later on you can even check within Revit itself on how the sections look like, the modified sections appear. So that is it for today's presentation. We here at Midas thank you once again for having attended this presentation, and we hope that you found this useful. If you have any questions or if you have any queries, please feel free to let us know, and we will be happy to, please feel free to just type it out in the questions box, and I'll be happy to address your queries.